finish out 3.1, and let's introduce the last of these three top trait functions. This is all about the trait functions. And that's something called the tangent function. What is that? Again, back to the unit circle. Take everything in terms of the unit circle, and we'll understand how it's all connected very simply. And also you see Pythagorean's identity is also here as well. And what we do is we take a point on that unit circle, take a line and a point that it forms. Here's a point over here, and we draw the line. What we do is we're going to define, and this is some angle theta over here, we're going to define the tangent to be the slope of that line. So the tangent is defined to be the slope of this line. So the slope, when theta is 0, we get 0. When theta is 90 degrees, you can see that's an undefined tangent. It's a perfectly vertical line. It's undefined. And then over here, this is the positive slope, positive slope, infinite slope, negative slope, and you can see how that changes. Well, what is the slope? Well, remember, the slope is always equal to the change in y over the change in x of that line. So let me drop this a little bit. Let me drop a perpendicular over. We'll kind of use that momentarily. So the slope is always equal to, we'll call it m for now. In the US we call it m. Nobody's quite sure why we call it m, but if you go to Europe, sometimes it's called s, the slope, some lowercase s, sometimes it's called a. We use m. The best people know it has to do with a French word meaning modulus, and they think that might be where it came from. But what is that? It's always the change in y over the change in x. Now you're going to see in mathematics, we don't like to write a lot of words, so we use the lowercase Greek alphabet letter delta. So we use this for my change in. That means change in y over change in x. Now very shortly when you get to calculus, you will see that used exclusively. So that's the y value. So the change in y is nothing more than this distance there. But remember the coordinates of this point. What are the coordinates of this point? The coordinates of that point are the cosine of theta for the x and the sine of theta for y. So the y coordinate is nothing more than this height over here. So that's equal to the sine of angle theta. This distance down here is essentially what we're calling my change in x. And that's equal to the cosine of theta. So my tangent of theta, let's kind of write it over here. We take the tangent of theta, and I'm going to write it in this way. So, write it as, T-A-N. We'll only take the first three letters of theta, is then defined to be the sine over the cosine. That's the way it's defined to be. We're going to talk about that in a minute. Now you can kind of see some problems for the domain of this. As I said, we have a problem if theta is a multiple of plus or minus pi over, or an odd multiple of pi over 2. Because what happens, if theta is 90 degrees, that's undefined. If it's 270 degrees, it's undefined. So, because I end up with my x value being 0. Y is 1, but x is 0. 1 over 0 is undefined. If I come up over here, and my coordinate there is x is 0, y is 1. If I take 1 over 0, that's the tangent, it's undefined. Over here, I have x is 0, y is negative 1. Similarly, I have negative 1 over 0, also undefined. So we can see over here the domain of my tangent function is as follows. We have D, set all elements theta. Theta is going to be a real number. It could either be degrees or radian. I'm going to do it as radian measure, a real number, where theta cannot equal to an odd multiple of pi over 2. Odd, and I'm going to write this more succinctly, of pi over 2, or an odd multiple of 90 degrees. Well, how do I write an odd multiple? Yes, I'm going to show you the simple way of writing it mathematically to write an odd multiple. Well, I could write an odd number. How can I write an odd number? There's two different ways. I can take an even number, say 2 times n, that's an even number. Any number n times 2 is always even. And I can either add 1 or subtract 1 and make it odd. Let's just subtract 1. So if now n equals 1, 2, 3, plug in all those values, plug in 1, 2 minus 1 is 1. Plug in 2, 2 times 2 is 4 minus 1 is 3. So for different values of n, that gives me odd multiples. So for over here, my domain of my tangent, I'm putting just write d, is equal to the set of all elements theta, such that, again, theta is a real number, but it has restrictions. And theta cannot equal to, I'm going to put it as 2n minus 1. I'm going to put plus or minus, because it could be, I could go around in a counterclockwise when it's positive, or clockwise if it's negative. So it's 2n minus 1 pi over 2, where n equals to 1, 2, 3, etc. Well, it's a very complicated. That's one of our first very complicated domains, because we can see the slope of that line goes off to infinity. Now, what you can also see when we graph this function, its graph is going to look, kind of different. Let's kind of take a look at that. If I graph it, let's kind of put it over here. I'll just do it over here. Let's see what the graph looks like. We'll see the following graph. Now, if I go between, say, 2 of those values, which is problem, let's take a look. Here's my y, my x. So let's go over to here to plus pi over 2 and minus pi over 2. If you put this into your calculator, you will get something that looks like this. If I get close to that, I can't hit 90 degrees. It goes off to plus infinity. It's closer and closer. This goes to plus infinity. This goes to minus infinity. Now, I get out of that the first, quadrant 1 and quadrant 4. That's what puts me between. And say I go over here to another. Here's an even multiple. So this would be pi, and this is 3 pi over 2. Go back over here and minus pi and minus 3 pi over 2. This thing will continue and look like this. It is periodic, but in a different way. So it'll look like this. And over here, same sort of thing. So it's got this periodic nature, but it's going from plus and minus infinity. You can plug that into your calculator. You can plug that into, I would do Desmos a little bit easier, and you see. So that tells me what the range is. So the range here, I can get any real number out. So in here, my range, that's my output of my tangent theta. I'm just going to write it this way. It's all the values y. I'll put it as y, even though it's not y. Such that, in this case, y is any real number. I can get any number here, over here, in any of those ranges, if you will. My domain, however, is restricted. I can't have division by 0. Any value that makes the cosine 0 has to be removed, and that is an odd multiple of pi. 90, 270, minus 90, minus 270, all those odd multiples of pi. Okay, any questions on that? Now, one question I always had And we're saying, okay, why the name tangent? Where did you come up with that name tangent? Well, let's give you a little background as to why it's called the tangent. Why do we call it the tangent function? And this is, again, back to our unit circle with a little bit extra as well. And then we'll talk about how to get tangent values as well. So where does the name tangent come from? Tangent is kind of from a Latin, kind of to kiss or to just touch. So we have something called a tangent line. So if you have some sort of a curve, and you'll deal with this a lot in the calculus, you'll have something called a tangent line. It means it just touches the curve at a point. So for example, that would be a tangent line. It's a line that just touches or kisses, as they say, the curve at one point. So it touches at one point. So how do we interpret that from the slope of that line? Well, this is how we do it. I'm going to draw my unit circle again. Here it is. My unit circle, as best I can draw it over here. And let's draw our little line over here. And we know the slope of that, at some angle theta, is what I'm dealing with. So this is how I define my tangent function as this length over that length. It's not tangent to anything, but that's the slope of that line. But if we extend this out, and I extend my x out, because it's a unit circle, so this entire distance here is just at 1. That's of length 1. So if I extend it out to here, this will form a similar triangle that looks like this. Okay, that's a similar triangle. Now I know that if this value over here, let's take a look over here. This length here, that blue length, is the sine of theta. Down here, that's the cosine of theta. And we know that we define the tangent of theta to be the ratio of those two, sine over the cosine. Well, we know that this blue line has the same slope as that line. So this slope and that slope are the same. Well, what is the slope of this line? Well, the slope of this line, for the red one, so the red triangle slope of that same line put over here now, is this side, I'll call that length A, over this length here. So that slope of that line is A over, in this case, that distance there is 1. This entire distance here takes me up for the unit circle, A over 1. Well, this is nothing more than the slope, so that's the slope, and we're calling that the tangent, so that's equal to A over 1, so that means A is defined as tangent. The tangent is nothing more than the length of that side of this extended triangle that is just touches the unit circle at that point. So for example, if I go out here, say this angle, I bring it all the way up to here, and the length of this line is tangent of that new angle, theta 1. And if I go even farther out here, well, I'd have to go way over here, and you can see where the tangent goes to infinity, plus infinity and minus infinity. So it's tangent because it just touches at that point. That's where it gets its name from. It's not obvious. You don't really need it, but sometimes it's nice to know where things come from. Okay, so what do you need to know at this point? You need to know what the domain and range of a tangent is. That's good. And just like we did for the sine and cosine, you need to know how to find those angles. So for example, if someone turns around and says, can you tell me what the tangent of, say, pi over 6 is equal to? Well, what I do is I rewrite that in my mind as sine pi over 6 over the cosine pi over 6. I put it back in terms of its definition. And then I figure out what each of those are. So I go to my unit circle. pi over 6 is roughly 30 degrees. So here I am at 30 degrees, and here I'm on a unit circle. Now the sine value is closest to a half, and the cosine value is the square root of 3 over 2. I plug that in, that's 1/2 divided by the square root of 3 over 2, which I take and rewrite that as 1/2, I'll write it this way, divided by the square root of 3 over 2. Division turns into multiplication by the reciprocal, so I put that as 2 over the square root of 3, so that cancels and just gives me 1 over the square root of 3. Very often you will see that rationalized, meaning you get rid of the radical. So you've learned in your previous algebra course that you can actually rationalize that denominator. This is fine. That's okay. That's perfectly acceptable. It's like 2 times 1.866. We won't worry about that. But it's, in this case, the square root of 3 over square root of 3 times the square root of 3, 3. So either this form or that form. And that's how I do it. Very simple. You can do all that for anything. Now, what happens if, you can do that for any of the angles, degrees or radians. Just plug it into your unit circle and figure out your, the same thing. 1/2 square root of 2 over 2 and square root of 3 over 2. Those are the only 3 choices you have, unless it's at that point or at that point. For example, now if someone says, what is the tangent of 90 degrees? Well, here I am at 90 degrees. Well, my x-coordinate, my cosine, is 0. So that's equal to kind of 1 over 0, which is undefined. So that's where it's not defined, because it's a odd multiple of 90 degrees, or pi over 2. That's very simple to find those angles, just like we did for the sine and cosine, but now you find both of them and take their ratio. It's always the sine over the cosine to get the slope of that tangent line. Okay, and the other thing you should be able to do is, if you have, these are exact values, but you should also be able to use your calculator to find approximate values. So if someone just gives you the following, let me put it in 2 different ways so you understand. You got to be careful here. This is going to be using a calculator. So now using your calculator, when it's not an exact value, to find approximate values. They're very often used in your engineering classes and your physics classes as well. Say, for example, you have the following. They have the tangent of 67. And you got to understand, what does that mean? This does not mean 67 degrees. If it doesn't have the degree symbol, it does not mean that. If you want 67 degrees, this is 67 radians. So if we know, go around 2 pi, that's equal to 6. This is like more than 10 times around the unit circle, and then where it ends, as opposed to tangent of 67 degrees. Now let's take a look at both of those on your calculator. You see they are not the same. You have to be careful when you're doing these problems when they come up. So I come over here. Now I noticed the last time I had this set for degrees. So now if I put in tangent 67, thinking it's 67 degrees, I'm going to get the wrong answer. This is not the wrong answer, because this is actually 67 degrees, even though here it looks like what I'm putting in, tangent 67. That's the tangent of 67 degrees, which would give me that value. Now if I truly want 67, this is 67 degrees right now, even though it's hard to see. But if I wanted it instead to be, I'll put this to the variation over here, just so you can see the picture. This is the 67 degrees, but it looks like this on the calculator. So if I looked over here, here's my unit circle, and I go up to like 67 degrees and draw my tangent. And this is length 1. This length here is approximately there, 2.36. That's 1, 2, and a little bit more. And that length of this entire side over here, make it go down all the way to the bottom, is at length of that tangent side is that. Now, if I truly want 67 radians, then I have to change my calculator over here and put it in the radian measure. Now when I look at it, that's identical. It looks like the same. And I put the tangent of 67. This is now radians. So in this case, I get radian measure. This is approximately equal to 1.65. Now, what is that? Well, I go around 67 radians. Every time I go around, remember 2 pi is approximately equal to 6.28. So if I go 10 times around, that's 62.8. So 10 times around 62.8, I need to go another almost 6. So it's kind of going around a unit circle multiple times. So here's my angle. I'm going around 10 times, 10, 10, 10, and then 10 puts me at 62.8, and then I have to go out another, fraction thereof, so it puts me probably right around here. Another pi over 2 would be 60, probably right about here. And if I look at the tangent, if I go over here, I'll be right about here. It's going to put me at this value. That height over here now is 1.65. So it's different. So when you use your calculator, always go and look at your, if you will, your other things. I'll put it over here just so you can see. Here's the other one. There's my tangent 67. If I go around here, I go around 10 times and then a little bit further, and it puts me out here, and that height, the length of that line is about 1.65. So anytime you're using your calculator with trig function, check your mode first. Usually that's where your mistake occurs. Check and see, because you might have left it from degrees or radians. Make sure it's correct. No symbol, it's interpreted as radians. It doesn't need a pi to be radians. It just has to be a number, any real number. Here you need the degree measure. Okay, so that's everything we know, what I need to know about our trig function. Okay, so let's move on. I'm just going to briefly mention, like I said, I'll mention in 3.2, we're not going to do any problems. I'm mentioning this because you will see these alternative trig functions. They're the reciprocal trig functions of the sine, cosine, and the tangent. So I'll put them down here. This is all I'm going to cover. I'm not going to give you any problems, but we will see these other functions from time to time. Their domains and ranges are much more complicated. That's why I don't want to go into those. So we have the basic trig functions that we've already discovered. We have the sine of theta, we have the cosine of theta, and the tangent of theta. Now for these three, that encompasses everything you know. In addition, we have what we call the reciprocal functions. And that means we have something called 1 over the sine of theta, 1 over the cosine of theta, and 1 over the tangent of theta. Well, in the US and in Europe a lot, but not in the eastern part of Europe, they don't. They give these special names. 1 over the cosine of theta is called the cosecant of theta. And you kind of write it as CSC of theta. That just means 1 over the sine. The 1 over the cosine is called the secant of theta, and it's written as SEC of theta. And then 1 over the tangent is the cotangent, and you just write it as COT of theta. Now sometimes people say, well, how do you remember which is which? Well, it's kind of easy if you look at it carefully. If it's the sine, the S and the C, the opposite go. The C and the S go. Cotangent is easy, it's just a reciprocal. And this is the cotangent is the reciprocal, which is nothing more than the cosine of theta over the sine of theta. So it just flips that. But that's all you need. These are the three additional functions, if you will, that are associated with the trig family of functions. But I remember the 1 over sine, well, s and c go together, so it's a cosecant. 1 over the c for the cosine, the c and the s go together, so it's secant. Very easy way. That's all we're going to do from 3.2. I'm not going to talk about their domains and ranges, which are much more subtle because they're kind of the reciprocals of these and they get much more complicated. Okay, so that's all I want to do is just to mention those functions. You will see, and we'll look at later on, some trig identities that involve secants and tangents and cosines and sines, essentially starting from the Pythagorean identity and then incorporating some other identities as well.